Yeah, so the same as this morning, we'll just go through these exercises. I'll give you some time for each one. So you do have access to this notebook, but yet again, try and I'll share the question on screen, and then try and do it without opening up that notebook, and then we'll go through the answer when everyone has tried it. So the first exercise 4 asks to integrate the sine of x between pi and 2pi. And then after that, to prove the fundamental theorem of calculus for fx equals x squared, which is the theorem that can just to show that the connection between derivatives and integrals. So you guys can start these two exercises. If you have questions for me to go into more specifics about the questions or other things that Professor Francesco asked about, ask them on the Slack channel, and then I'll talk about them until everyone has finished the first exercise, and then we'll go to the next one. Cool. I see there is already a question here in the Slack. So singular value decomposition up-down is definitely also possible in SymPy. And the Cholesky decomposition, I'm pretty sure you can just do something like the matrix.Cholesky. And I think the other one is the matrix.singular or something like that, but you can do that. Mizakwa, your question about how do you do the vector autoregression too? I'm not sure what that means. Does it refer to some kind of linear regression or some kind of machine learning thing? I'm not familiar with vector autoregression, so maybe you can be more specific, and then I can look that up for you. Yeah, the font, of course. Okay, I think that should be fine. Let me know if I should make it bigger. Are you guys winning with the exercise? Do you want a bit more time, or can we go over it? Do you have it? Let me know in the Slack channel if you guys want more time. Otherwise, I'll go over the answer. Give it like 1 more minute, unless someone asks for more time. Okay. Yeah, it looks like we can go look at it. So yeah, I think these examples were touched upon in Francesco's lecture. So the integrate, you just call the SymPy integrate function with the specific mathematical function, so the trigonometric function sine of x, and you specify the range. That's pretty simple, and then it gives you the area under the curve for sine of x. And then the fundamental theorem of calculus, you could have done a few ways when it's kind of just to show it, not to prove it, I guess. So you have your function, create as the expression, so like that. And then you just show that if you integrate the function and store that as another function, so this would be the integral of f to x, and then the integral looks like that, and then if you differentiate it again, you get back your original function. So that just shows the connection, which is what the fundamental theorem of calculus says. You could have gone the other way around as well. If you just differentiate f, which is x squared, go down to 2 of x, and then if you go back up again, you get the integral, which is x squared. So just a way to check with SymPy that the theorem still holds and we didn't break math. So yeah, you can try out exercise 5 then, just the series expansion of cos h to the 8th order. I'll give it like a minute or two and then we'll go over the answer. And if you guys have any other questions, feel free to ask. Okay, this is an easy one. Can I go over the answer, or does anyone want more time? Okay, I'm gonna go through the answer since you like no one wants more time. So yeah, you just define a series of the cos h function, and you give it the range. So that's just how Francesca showed. Oh, really? Can anyone else not see my screen also? Do you guys not see a notebook? Okay. Maybe it's something with your connection, Revarsha. When I started, I first shared the wrong screen, which was the screen with the Slack on, and then I changed it. So maybe it's frozen for you and you just have audio now. So you can try and rejoin. Because the others seems like they can see the notebook. Okay, cool. No worries. So yeah, this is again just a normal series expansion. You get your error term. Yeah, it's just calling a function and giving it the range with the order that you want, and it calculates for you, which is nice. Okay, cool. See, we're good with the screen. Okay, and then yeah, these exercises are a quick. So this one is just about the linear algebra that Prof touched on in the end. So given two vectors, find the component of u in the direction of n. So this is the same as finding a projection of u onto n, which there is a formula for. So yeah, see if you can do that. These are the vectors, and then we'll look at the answer. And feel free to ask like questions if there's something about the question you don't know, or yeah. Yeah, are you guys winning with it? Let me know if you want some more time, like a few more minutes, or if you're done, maybe say in the Slack channel you're done, then I can go after the answer, go over the answer. Okay, so last chance if anyone wants more time, otherwise I'm gonna go over it. All right, looks like these are easier than this morning's one, where everyone's done. Yeah, so finding the projection of u onto n, or the component of u onto n. Yeah, so there's a formula for this, which looks like this. You take the dot product between u and n, so your two vectors, and you divide by the vector you're projecting onto's length squared, and you find all of that with the vector n. So this is the kind of the magnitude, and then this is just it in its direction. And do I have that here? No. Okay, yeah, so this is just the normal formula. So if you got 5, 5, 5, that's the same. You could have done, instead of u norm squared or n norm squared, you could have also done n dot n, which is the length squared. So I think that's the more used formula in text. I don't know. Okay. And then, yeah, now just to find the eigenvalues of a matrix. So this given a matrix A that looks like this, find the eigenvalues and get and then diagonalize it. Yeah, so get that decomposition where the eigenvalues are on the diagonal. Okay, and yeah, that's the last question. Okay, is everyone happy with that? Yeah, just send a message if you want more time, otherwise we'll go over it. It's again, just function calling, really, just to show those. Yeah. So yeah, to get the eigenvalues and eigenvectors, this is the same. More time. Cool. Wait. Cool. Yeah, if anyone wants more time, just send a message. Otherwise, I'm gonna go over it. Yeah, so just getting the eigenvalues and eigenvectors, since this is already a matrix object for SymPy, all of those properties of the matrix you can compute on the fly. So to get the eigenvectors, you just call the eigenvects function, which gives you all the eigenvectors, and the eigenvalues. The eigenvectors are the ones here in this vector form, and this is just the amount that scales it by. And then to do the diagonalizable decomposition, you just call the a dot diagonalize. So, which you get then two matrices, one with the eigenvalues and one on the diagonal, which is this L, and then Q. So when you have this, yeah, you just call this function. And when you have it, you should be able to multiply them together to get the original matrix again in the right order. Yeah. Cool. So yeah, now you have a nice, more efficient way to store the important information of your matrix in terms of its eigenvalues and this other matrix. So yeah, that's all the questions for this tutorial. If you guys have any questions, just feel free to ask on the Slack. And then, yeah, otherwise then have a nice afternoon further. Hope you learned a lot today. SymPy is pretty cool. So it's, I think it's very useful things to learn, which you can apply anywhere, really. So yeah, send through any other more questions on the chat. Otherwise we can, yeah, stop. Okay, doesn't seem like there's any more questions. Yeah, then I'm gonna stop sharing. And yeah, thanks for joining, guys, and see you tomorrow. Bye-bye.